Potential energy is a way to think about kind of storing energy. In other words, it's one of these accounts or one of these buckets we can put energy that we can move it in and out of. So potential energy, like I said, can be thought of as stored energy. That's where the name comes from. It's a little challenging. There can have some issues if you get too caught up with this, but generally speaking, it works well. It's an energy system that easily allows energy to be added or removed. In other words, it's relatively easy to put energy in or take energy out. The physical change that's associated with the change in the energy system is one that can go back and forth. So there's two types of potential energy. The first is gravitational potential energy, or GPE. This is the energy associated with the position of an object related to the Earth. So if something is farther from the Earth, it has more gravitational potential energy. If it's closer to the Earth, it has less gravitational potential energy. And this can be written as the change in GPE is equal to the mass of the object times g, the acceleration due to gravity, times the change in height, where this is the distance from the Earth. And technically it's distance to the center of the Earth, ish, but since we're always looking at changes in height, we can just pick anything to be 0 and just say, oh, I went up by 10 meters or I went down by 10 meters. Next, we have elastic spring potential energy. This is the energy associated with the stretching or compressing of a spring or something else that can stretch or compress. The change in the spring potential energy, or the change in the elastic potential energy, is equal to 1/2 K, and I'll talk about K in a second, times the change in the change of x squared. This one's really weird. It'll be something that we kind of probably will talk about in class directly. K is the spring constant. And this is the stretchiness of the spring. So if a spring is really stretchy, it has a low spring constant. If it's very easy to stretch or compress, low spring constant. If it's very hard to compress or hard to stretch, high spring constant. This is just calculated by stretching and seeing what it is. It's determined experimentally. There's no equation for it, and it will usually be given to you in a problem, or you'll be asked to solve it. This delta x in here is how much stretched or compressed from equilibrium. So if you've ever looked at a spring or played with a spring, you know there's like a normal position that, like if it's just sitting by itself, that it'll sit in. That inner delta x is if I stretch it some distance or if I compress it some distance, that's the delta x. So it's not how long the spring is, it's how much the spring has been stretched or how much the spring has been compressed. And we want to compare two of those positions. So if it's not stretched or compressed, this delta x is 0. And then if I stretch it out to 5 centimeters, now it's 5. So the change would be 5 from the final stretch down to 0, the initial stretch. And the example, I think, will also help clarify that. So first, how much work must be done to raise a 20 kilogram box a distance of 10 meters? So in this case, we have a box, and we know that it's going up some delta h equal to 10, and it's going up, so we know that we want a positive delta H. And the mass is equal to 20 kilograms. So this is a nice simple delta GPE is equal to work, because remember work is changes in energy, so if we want to change the GPE, we need to do work on it. So the work is equal to change in GPE. Work is equal to mg delta H. Work is equal to 20 kilograms. I'm going to use 10 because it's easier to do the mental math, times 10 meters. Kilogram, meters times meters is meters squared, divided by seconds squared. This will give us joules. So the work is equal to 100 times 2, 20, hundreds, 10, 2,000 joules, or 2,000 Newton meters of work must be done to raise it that distance. Example 2, a spring has been initially stretched by 20 centimeters from its resting position. How much energy is added or removed when changing this stretch to only 10 centimeters? Assume that the spring constant has a spring constant of 0.4 newtons per meter. Okay, so let's draw a diagram because this will help. We initially have a spring that's been stretched 20 centimeters. Then after some point later, it's only been stretched half as far. So this is the initial stretch. This is the final stretch. So it was initially stretched 20 centimeters, now it's stretched only 10 centimeters. And this right here would be our equilibrium, or our kind of natural resting position. So we know that the change in spring potential energy is equal to 1/2 K times delta of delta X squared. So this is equal to spring potential energy is equal to 1/2 K times the delta X final squared minus the delta X initial squared. Because we have this outer function, this outer delta applies first. So now we have change in spring potential energy is equal to 1/2 times 0.4 newtons per meter times delta X is 10 centimeters. So 10 centimeters, which we need to convert to meters. So let me fix that right now. This is another reason we write in our units as we go, because we catch things like recognizing that the units don't match. So 0.010 meters squared minus 0.02 meters squared. This is 0.2 newtons per meter. And then this is going to be 10 squared would be 100. So it would be 0.1. My brain's struggling with that. 0.01. Sorry, these shouldn't be 0.01. These should be 0.1. It's centimeters and 0.2. So 0.1 squared would be 0.01. That sounds right. Meters squared minus 0.02 meters squared equals, this is going to be negative 0.01, so this will be 0.02 joules. And it's got a negative sign on there. So in other words, the spring loses energy as it goes to this shorter stretch. And that kind of makes sense because, you know, it's going to a relaxed state. It's releasing that energy from the spring. If you want to check the units, we have newtons, which is a kilogram meter per second squared. So the meter from the Newton is going to cancel to meters here, which gives me kilograms per second squared. And then I get this meters squared, which changes me back to joules.